Alright gang, here we go. So this is Chem 1, Unit 4, Part 5. We're talking about intermolecular forces. So I thought it'd be fun to start off with like a little comic here. So you got a polar bear, okay, and a grizzly bear, and I don't know why they're hanging out together, but they are. Okay, and the polar bear says, "Help, help, I'm dissolving." And the grizzly bear says, "Well, but bears are insoluble. Insoluble means it doesn't dissolve, right?" And the polar bear says, "It's easy for you to say, you're not polar." Okay, so that's the joke here. All right, and so the idea is that when you're deciding whether or not things are going to dissolve in something else, you have to look at what intermolecular forces are being are interacting between the two. And since polar bears are polar, and so is water, they both have that in common, and so the polar bear will dissolve. It's not, it's a stretch, but it's kind of funny. But anyway, so intermolecular forces. Okay, so there's two different types of forces, and we've talked all about intramolecular forces so far. Okay, intramolecular forces are the forces that form the bonds within a compound. Okay, they are always stronger than an intermolecular force. Always, always, always stronger than an intermolecular force. And we have, so far we've divided those into either covalent bonds or ionic bonds. All right, those are the two types we've talked about today, or so far in this chapter: covalent and ionic. All right, so everything we've talked about so far are intramolecular forces. Today we're talking about intermolecular forces. Intermolecular forces are the forces. Forces, and they're not really bonds. This is not a great word. They're forces or interactions, okay, between compounds, different molecules. They're always weaker. All right. There's lots of different intermolecular forces. You'll also hear me refer to these as IMFs. All right, intermolecular force. Okay, and we're gonna focus on three. We're gonna talk about dipole interactions, hydrogen bonds, and dispersion forces. All right. So dipole forces occur when two polar molecules are attracted to one another. All right, so we're going to look at this example once we kind of talk about it here real quick. So remember, back when we talked about polarity, we kind of remember we talked about these two different symbols, partial negative and partial positive, these deltas. And they kind of tell you like which side has more electrons versus the other, right? And so that you've got the molecule that has a positive end and a negative end. And we know just from, that like opposites attract, right? So if you have a molecule that has positive ends, then that's going to be attracted to the negative end of another molecule. All right, and so because these opposites attract, these guys will like start to form interactions, kind of like two magnets that get stuck together. And that's actually not a bad way to think about it. Is that when you stick two magnets together, you can, those magnets get pulled together. And then think to yourself real quick, well, which one would be easier, ripping a magnet in half or just pulling these two magnets apart from one another? The bonds that are holding the magnet in itself as a clump of magnet, that is an intramolecular force, right? Those are the forces that are holding that magnet together within itself. The intermolecular forces are the forces, those magnetic forces that are pulling those molecules together. And so it's easier to break those intermolecular forces, all right? So specifically, right now, we're talking about these dipole forces. So remember, dipole, means two and pole means polarity. So you've got these molecules with these two poles, right? One that's positive, one that's negative. And so what happens is that these molecules will orient themselves and then attract each other to the positives and negatives so that they line up together. So here you've got the negative end of one molecule lining itself up with the positive end of the other molecule, and they get kind of attracted to one another. All right, down here, you could, so here's another way to think about it. So this was how they kind of line up linearly, and then this would be how they line up like on top of one another. So notice how this might be even stronger than this one over here, because here you've got a negative and positive attracting each other here, and then over here you got a positive and negative attracting each other over there. Okay. Those kind of an interesting idea. So those are called dipole forces. So if you're deciding whether or not something has dipole forces, really what you need to do is see whether or not your molecule is polar. Okay, and so if you worry about that, go back to the last video and do those practice problems. All right, so boiling points of fluorine and hydrochloric acid. Remember, fluorine is a diatom, so it always comes in sets of two. The boiling point for fluorine is, let's see, I had it pulled up, is a negative 188 degrees Celsius. So that's pretty dang cold. Yeah, negative 188 degrees Celsius. Yeah, it's not gonna, be pretty hard to have liquid fluorine. And then the boiling point of hydrochloric acid, let's see, I had that pulled up as well. The boiling point of hydrochloric acid on the flip side is 108.6 degrees Celsius, or 227 degrees Fahrenheit. So that's boiling point of acid is even high, of hydrochloric acid is even higher than water, which is kind of an interesting idea in and of itself. But anyway, so we can explain this by talking about dipole forces. All right, fluorine. Remember, so with fluorine, you've got two fluorine molecules, and because it's two things attracted to each other, the electronegativity difference between these is zero, right? Zero electronegativity difference, and so therefore, this molecule here is completely nonpolar. All right. Now hydrochloric acid on the flip side, right? Hydrochloric acid, we did this in a previous video. This guy has a polarity, right? It's got, one end of it has a partial positive and the other one has a partial negative charge. Remember, just to refresh, we can also draw that by doing this. Remember, this shows that the electrons are being pulled this way, and this end is a little positive on this end, showing us that this is electron deficient. So anyway, so this has polarity. So these bonds here are going to be stronger, and so these molecules are going to be harder to break up. So anytime, the idea is that when you're boiling something, what you're really doing is making those molecules get farther apart. Remember how we talked about how liquids and solids, right? Liquids and solids are mushed closer together, and really it's the idea of how far apart can they get, and they can get farther and farther apart depending on how much energy they have. Okay, and so these molecules can get farther apart depending on how much energy they have, and this energy is really dependent upon how hard are these molecules stuck together. Okay, and so because hydrochloric acid is stuck together harder, okay, it's harder to get apart, so therefore it takes more energy, so you have to crank it up the temperature. Okay, and so then as they turn into a gas, they can get farther apart, and so that means they have more and more energy. All right, so hydrochloric acid has a higher boiling point because it's polar, whereas fluorine has a lower boiling point because it's nonpolar, and it's really easy to break up those fluorine molecules one from another. Now remember, we're not breaking up those molecules themselves. Like, the two fluorines are still stuck together, and the hydrogen and the chlorine are still stuck together. What we're doing is we're making sure that if there were two sets of them, like two fluorines, or two sets of F2, that it's easier for them to spread apart from another. Okay. The next one here is hydrogen bonds. All right, this is specific, like essentially it's a dipole interaction, but it's a stronger version of a dipole interaction. Okay, and these can only happen when you have a hydrogen that's attached to a fluorine, oxygen, or nitrogen. All right, fluorine, oxygen, or nitrogen. This is how I remember it. I say it's a hydrogen bond, so you need hydrogen. That's why it's called hydrogen bonds. All right, and then it needs to be with FO or N. Okay, because FON spells fun. Yeah, that's right. FON spells fun. But anyway, so you got hydrogen with FO or N. So if you got a hydrogen attached to one of those three things, you have hydrogen bonds going on. Now this is kind of a misnomer, this idea that it's a bond. Even though it's called a bond, it's still not nearly as strong as a covalent or an ionic bond. So it's still kind of a different idea. We call them bonds because they're stronger than any of the other intermolecular forces, but still compared to like an actual covalent or an actual ionic bond, these the hydrogen bonds still aren't not nearly as strong. Okay, it's the strongest type of intermolecular force, and it explains many of the different properties of water, and we're kind of look at those in class, and next semester we'll go into those much more in depth. But the idea is that you've got hydrogen, okay, right? This is our water molecule. You've got this hydrogen attached to the oxygen. So between different water molecules, you can have hydrogen bond going on. All right. So NH3 versus pH3, the boiling point of NH3, let's see, I had that pulled up. Boiling point of ammonia, that's NH3, is negative 28. Oh, that's in Fahrenheit, though. Stupid Google. Negative 33.34 degrees Celsius. And the boiling point of pH3, this is phosphine, is negative 87.7 degrees Celsius. All right, so it's not nearly as drastic as the last one we looked at with the dipole interactions, but there's still quite a bit of a difference here. So notice that now, remember they're negative, so it works a little bit, it works backwards from positives. So the ammonia has a higher boiling point, right? It's closer to 0 than the phosphine, pH 3 here. Okay, and the idea is that because NH3, you've got these hydrogens that are attached to these nitrogens, you can have hydrogen bonds. But between phosphine, you got hydrogens attached to phosphorus, so you can't have hydrogen bonds because this hydrogen, because the phosphorus is not FO or N, right? So here's another example to kind of show you here. Remember, intermolecular forces are between different molecules, okay? And so you got this hydrogen bond that's occurring between the hydrogen of one water molecule and the oxygen of the next, and they kind of form this pattern here. And notice how, because of the shape of water molecules, they kind of get, notice how some of them are kind of sticking in and out of the page, whereas some of them are parallel with the page and stuff like that. And so this also explains kind of how why water molecules, why snowflakes make the shape they do, or ice cubes make the shape they do, and so on and so forth. And we'll talk about that more in the future. But anyway, so here's hydrogen bonds. Notice how water is special because it has two places that you can make hydrogen bonds, whereas like the ammonia and the the ammonia we just looked at, NH3, only has one place. All right. Last one we talk about here is London dispersion forces. They're also called van der Waal forces. All right. So London dispersion forces are super ridiculously weak. All right. The idea is that it's not a force that's permanent. Okay. With dipoles, like if a molecule has a dipole, it always has a dipole. If a molecule has hydrogen bond ability, it'll always have that. With London dispersion forces, it's a temporary force. So it's something that just kind of happens and then it goes away. All right. And we'll kind of explain what that means. All right. So the idea is that that like you've got your nucleus right here, right? And you've got, your electrons around it, okay? You've got your nucleus and your electrons around it. And so these electrons, remember, this electron cloud is like a probability zone. It's an area where it's likely to find an electron. Well, these electrons are moving around like crazy. So it's a possible, right? So, most of the time your electrons are going to be like one on the other like this, right? You're going to have an electron over here, you're going to have an electron over here. But it's also likely that what might happen is both of your electrons are going to be on one side. Well, if both of your electrons are on one side, it forms a temporary dipole where this side's negative because it's got all the electrons. This side's positive, so it's got all those electrons over there. So it creates a temporary dipole. Okay. Once that occurs, it kind of cascades and makes all the other molecules around it also have dipoles. Oops, wrong way. So here's kind of a representation. So you've got these two neutral molecules, right? So no dipole happening here. And so they really shouldn't be attracted or repelled by each other at all. But what happens is, look, all of our electrons ended up on this side. So we got this delta negative, this partial negative on this side, partial positive. And so when that happens, you got your partial positive. Well, this forms partial positive. So these electrons that were in this right molecule here, they're going to be like, well, shoot, dang, that's a positive. I like positives. So then all the electrons that were over here are going to be like, well, shoot, dang, we're going to go over here, and they're going to move over here, right? And so then you get this temporary attraction where the positives are over here and the negatives over here. And notice that you got this dipole interaction, positive, negative. And then eventually, like, this lasts for just a very, very short amount of time, and then they go away. All right. Oops, wrong way. So the idea is that the more electrons that you have and the bigger, the squishier your molecule is, the more your dispersion force is going to increase. Now, it's still ridiculously weak compared to the other intermolecular forces. That, like fluorine, for example, remember fluorine boiled at a stupidly low temperature, and fluorine only has London dispersion forces acting on it. But the interesting thing is all molecules always have London dispersion forces. So even ones that have, so if I ever ask you to list out, here's a molecule that has, list out all the intermolecular forces that are possible with it, you better have said London dispersion forces for one of them. So anyway, so that's intermolecular forces and that stuff. So do those practice problems. They can be kind of tricky to think about, so make sure you're really thinking about what you're doing, checking your answer on the answer key. Let me know if you have any questions, and I'll see you on the flip side.